Swayam Prabha. Digital India. Educated India.
Welcome again to the course on embedded software design and validation. From the last lecture, we had started our discussion on hardware synthesis. Essentially, our objective is to understand or learn embedded software design strategies for hardware synthesis. We will start from where we had left in the last lecture. We will complete that and then have a look into scheduling strategies for within a basic block for hardware synthesis. So, in the last lecture we were seeing the overall steps in high level synthesis or architectural synthesis, which takes the design from the architectural level to the register transfer level design. Okay. So, we said that in high level synthesis we first decompose the model or the model of the application that is to be designed in hardware into basic blocks, and we need to generate the master controller. In order to do that, what do? We take the HDL or the hardware description language code, we extract a flowchart structure from that code, and from that flowchart structure we generate the control flow graph. In the control flow graph, each node is a basic block and edges denote transfer of control within basic blocks, right. So, an edge, so a node will be a basic block. And what are basic blocks? Basic blocks are straight line sequences of code with no in simple terms, basic blocks are straight line sequences of code where control cannot come from anywhere else in the program at any intermediate statement within the basic block, and control cannot also bifurcate into multiple flows of control from any intermediate statement into the basic block. So, there could be multiple flows of control at the input of the first statement of the basic block, and then all these sequences of code will be executed one after another in straight line sequences and and then after the last statement of the basic block there could be again multiple flows of control emanating out of the basic block node. Okay. So, this is the description of the basic block. So, essentially they are straight line sequences of code, and we said that from this control flow graph we can directly obtain the master controller. Essentially what the master controller will tell me? The master controller will tell me that control will come from these places into a certain basic block, and then control will go to some multiple other nodes from a given node. Suppose if this one is a node, and the control will say that from these nodes control will come to this basic block, and to these other nodes control will go to some other nodes, right. This it will say. It could also say that these two nodes is an OR, in the sense that either the control will flow either to this node or to this node, because there is an if statement, let us say, depending on the condition truth or false, means depending on whether the condition is true or false, either this edge or this edge will be followed. So, all this information is available within the control flow graph, and essentially the master controller also has this information. Okay. Then what we will do after we have understood that after we have the entire control flow graph and the entire master controller, then we have to schedule operations within a basic block. And we said that essentially all operations within the basic block can be scheduled within the same clock cycle, but having to schedule all operations. Why can it be scheduled in the same clock cycle? Because there is no control flow branching within a basic block. The control flows in a straight line sequence. So, it is only a data flow, there is no control flow, it is a data flow. So, therefore, the operations within the basic block can be represented only as flow of data. So, we can say that A plus B equals to C or C equals to A plus B, that means the data in A and the data in B will be added and it will go to C. Next control will flow, you can let us say you can say that E equals to C plus D, right, and then likewise the control will flow, and essentially it will only be a data flow, as we will see in subsequent examples. And because it is only a data flow, we can have it only using combinational circuits, and all operations can be executed within the basic block in the same clock cycle, because the control will flow at the beginning and data will sequentially be processed one after another, and then control will flow out of the basic block, and all the operations can be done one after another, possibly in different functional obviously in different functional units within the same clock cycle can be performed. However, if we do that, then if the basic block size is big, then there will be, let us say if you have 10 instructions or 10 operations that are performed within the basic blocks one after another, then all these 10 operations, and these operations have data dependencies, then all these operations will happen what in a sequence one after another. So, you will require say 10 different functional units, and the output of one functional unit goes to the input of another functional hardware functional unit, and therefore, the length of the clock cycle has to be at least equal to the aggregate length of all the propagation delays of all the functional units in this basic block, because the data flows sequentially from one functional unit to another, because you have data dependencies among the operations within the basic block. However, there are no control flow dependencies, only data flow dependencies. Okay. Now, so we also said that however, if we have that, there it will be the clock cycle will be arbitrarily long, which we do not want, because the same clock cycle will feed other basic blocks which could be smaller in size, let us say, and therefore, after completing their operations they will have to wait for a long time, because the length of the clock cycle has been chosen to be large. In order to avoid that, we have to embark onto the process of scheduling. So, scheduling assigns a start time to each operation in the basic block, and then after you have assigned, we will take examples and see into all these things in greater detail. After you have assigned the time steps to each operation, we have to generate controller. We have to generate a controller to control so that to have the control that what the schedule has told me, that certain operations should be performed in certain time steps, they should actually happen in those time steps. We need a controller, and that controller, the controller that we have within the basic block, that is again then embedded within the master controller. And then after for all the basic blocks we have their individual controllers embedded within their basic blocks, we can generate the overall timing for the overall application. So, now we have the control flow graph or the master controller. Within the master controller we have within the master controller we have nodes, and those nodes are basic blocks. We have ascribed time steps to operations within the basic block using scheduling, and then we have a controller to control that those operations within the basic block actually happen at those time steps, and after we have the controller for each basic block, we embed the controller for each basic block within the master controller. Now, when we have the master controllers for all the basic blocks embedded within the master controller, so for within the master controller for all basic blocks we have embedded the controllers for each basic block, then we can ascribe overall global timing to the entire application. Okay. Okay. So, after this we will look more deeply into the scheduling process. So, given a basic block, we obtain a data flow. So, we said that it is a data flow graph, there is no flow of control. Let us say our basic block has only this statement, the following statement here, this statement. So, x plus y into z less than w plus t. So, this can be represented using this data flow graph. So, here what is happening, let us see y, this y and this z, we have this operations multiplication that performs y into z, and then the output of this is then added to x. So, the output here gives me what? This gives me x plus y into z. Okay. And then from the other side w plus t. So, here we get w plus t, and then we have the less than operation, comparison operation, and at the output of this we have the truth or falsity of for this particular statement. The output will tell me whether this condition is true or false at the output of the comparator, right. So, this one is a data flow graph and it represents this basic block here. So, in the data flow graph of a basic block, the nodes are operations. In the control flow graph, the nodes were basic blocks. Within the data flow graph of a single basic block, the nodes are operations, and the edges denotes data dependencies, which means that here you see that you have a dependency that this plus operation can only be performed after the multiplication operation between y and z has been performed, has been completed, right. So, the edges denote data dependencies. This is an acyclic graph, it provides a partial order among operations. So, there are many correct partial orders, that means all orders which satisfy precedence relationship, data dependencies, those are correct partial orders. For example, here a partial order could be we could obtain multiple partial orders. For example, we could say that, let us say if all these operations were performed in the single sequence, then you could say that you will have the multiplication in a single, let us say functional unit, there is a hypothetical functional unit that can perform everything, then you can have this plus operation, and then you could have the other plus operation, this one we could have this operation followed by this operation, then followed by this operation here, the next plus operation followed by this operation, and here you have y and z, here you have x, here you do not require this this edge, because there is no dependency between w cross t. However, if you for the sake of the order I have given this, said that this is also a correct order, you will have these two. This is not a data dependency, by the way, not a data dependency, this is not a data dependency. Here you have w and t, and on the output then this is again another dependency. However, what will happen is this, the output of this will come here and the output of these two are data dependencies. However, this one gives me what? This one gives me x plus y into z, and this side this one gives me w plus t, and the sequence in which we have performed the operations, they all satisfy data dependency. Okay. So, if we had a single functional unit, let us say, that could perform both all the three, that means the multiplication operation, the addition operation, and the comparison operation, then we could have done this in separate time steps, and this would be a correct partial order. That means, in the same time step, in the same functional unit, in time step 1 we could perform y into z, in the second time step we could perform x plus y into z in time step 2, and then in the third time step in the same functional unit we could perform w plus t, and then in the same functional unit again in the fourth time step we could perform this comparison operation here, right, and hence this is a correct partial order. There could be, needless to say, there could be multiple other correct partial orders. Okay. Now, after we have obtained this data flow graph, we obtain from the data flow graph we extract the operation constraints graph. in the operation constraint graph, it only shows precedence relationships between operations. We do not require the variables here. So, for example, this is the dummy no-op, the start node of the operations control graph, and then we have two nodes, say two independent actually operations that can start. This the plus operation, this plus operation here, this one, this plus operation, this star operation here, and then from the plus depends on the star operation. So, it shows the dependencies, but it does not show the input variables or the output variables, right. So, it only shows the data dependencies. Okay. So, this will be called the operation constraints graph or OCG. So, in the data flow graph, we will remove the input and output variables, and then we will add a source, dummy source and sink node, and then directly from the data flow graph we can obtain the OCG. Okay. Now, before going into understanding learning scheduling strategies, exact scheduling strategies, we can see that different schedules that we obtained using scheduling strategies can have varying effect on cost and performance of the hardware design. For example, let us say that there are two schedules, these are two schedules, schedule 1 and schedule 2 for the same operation. In the first thing that we could say is that, see, in schedule 1 we have 3 time steps, time step 1, time step 2 and time step 3. So, this whole set of operations that we require can be performed in 3 time steps, right, 3 time steps, time step 1, time step 2 and time step 3, these whole setup. The same set of operations in schedule 2 can be performed in 4 time steps, time step 1, time step 2, time step 3 and time step 4, right, but this is the same set of operations. However, there is a difference. The difference is this, that you see here 2 plus operations are performed in the same time step, and we know that if they are performed in the same time step, I cannot reuse the same addition hardware resource, adder resource. I cannot use the same adder resource because both these operations are performed in the same time step. However, in schedule 2 we see that the two addition operations has been performed in different time steps, and hence this will require for this schedule we will require only one adder and one comparator. However, in this schedule we will require 2 adders and 1 comparator. However, so cost wise, in terms of cost, schedule 2 is lower in terms of hardware resource cost than schedule 1. However, schedule 1 means exhibits better performance, it completes earlier than schedule 2. Okay. Now, after we have done scheduling, we have to do resource allocation and binding. In resource allocation, what do? We mark hardware resources, mark types of hardware resources for each scheduled operation, right. We mark hardware resources. That means it also says, means this allocation is performed globally, not within the same basic block. So, there could be, let us say, there are multiple things that related to which optimization can be done in allocation. For example, it may be possible that more than one type of resource can execute the same operation. For example, for addition we could have a ripple carry adder and a carry look ahead adder with different cost versus performance trade offs. So, then which type of adder do we use? And this ripple carry adder can be shared among multiple addition operations, not only within the basic block but also across multiple basic blocks. So, for a given type of hardware resource, we choose different types of hardware resources and then assign operations to such types of hardware resources. For example, we could say that certain addition operations, a few addition operations will be performed in the ripple carry type adders, and certain other addition operations within of the application will be performed in the carry look ahead type adders. Now, when we have decided that which operations will be done in which types of adders or hardware resources, then we will do binding. That means, now let us say that we have 4 carry look ahead adders and 3 ripple carry adders. Then we will have to say which addition operation will be performed in which instance of a carry look ahead adder, that is binding, that is exactly binding an operation, a hardware operation onto a certain instance of a certain type of hardware resources. In allocation, we have decided on the types of hardware resources, types and even numbers of different types of hardware resources. However, which hardware resource instance, which hardware resource instance will perform which exact addition operation, this binding had not been done in the allocation step and is done actually in the binding step. So, binding maps operations to functional resources, Allocation and binding can be looked upon as a global optimization problem and not only within a certain basic block. So, we need to consider multiple basic blocks when performing allocation and binding. And then, as we said, lastly we perform in step 4, the FSM controller for a basic block is inserted into the master FSM controller, replacing the state of the basic block. So, within the master FSM, so we had, let us say, a basic a master controller like this. Let us say master controller, this one was basic block 1, this was basic block 2 and this was basic block 3, and then within this we now replace the controller for, we replace with the controller for basic block 1. When we have scheduled operations within the basic block, done some allocation and binding, after that we have the exact control, we can obtain the exact controller for the operations within the basic block, and then this controller will be embedded within the master controller basic block node. Okay. Now, we go into deeper into the scheduling step. So, we saw the overall operations within high level synthesis. We saw that we take the application, obtain the control flow graph, generate the master controller, go into the basic block, schedule operations within the basic block. After scheduling, we do an allocation, we do a binding and obtain the final timed master controller, and then after looking at this introduction, we will now go into scheduling in more depth. So, as we said, scheduling assigns time steps to each operation in the operation control graph of a basic block. Okay. Choosing a time step is an optimization problem, right, and has multiple attributes. For example, a schedule could be evaluated in terms of the number of time steps it takes. In the last schedule, we saw that we saw 2 schedules for the same set of, for the same operation control graph or data flow graph, and in one we had 3 time steps, in the other we had 4 time steps. We said that the one which takes lower number of time steps higher in performance. So, number of time steps is an evaluation criteria. Number of functional units or hardware resources required is also another criteria. Why? Because it determines the resource cost for hardware design. The number of temporary registers required, we will look at this later if time permits. Okay. There could be multiple other parameters or evaluation matrices for scheduling. Scheduling in hardware synthesis is primarily categorized into 4 classes: resource unconstrained scheduling, where you have where you assume to have an unconstrained number of resources. You can, during the design, you can assume that you can use any number of resources of any type, that is resource unconstrained scheduling. Time unconstrained scheduling, where you say that you have limitation on resource usage, but your time is unlimited, you can take any time, but any amount of time, but you cannot have more than a certain number or types of resources. Okay. You have resource constraint scheduling, in where you say that yes, you cannot you cannot use more than a certain amount of resources are constrained, and among all schedules typically what you try to do is to generate a schedule which takes the lowest time, however ensuring that it does not violate constraints on resource. Time unconstrained scheduling, it says that you have unlimited time, but you cannot have more than a certain amount of resource. Time constraint scheduling. For time constraint scheduling, you say that you cannot take more than a certain amount of time, and then your typical objective is to minimize the resources required, the amount of resources that will be required to, let us say, perform all the operations that are needed within the basic block with the least number of hardware resources. So, here in time constraint scheduling, you are given a bound on time and you have to perform all operations within this bound on time, and your objective typically is to use the least number of resources. Why? We said if you can use lower number of resources, lower amount of resources, then your design cost lowers. So, we look at the first type of scheduling strategy, resource and constraint scheduling. Reading the problem definition: schedule operations within a basic block such that all operations can be performed in correct sequence in minimal time using unlimited hardware resources. So, we need to perform all operations in minimum time using unlimited hardware resources. So, how do you do that? You perform a topological sorting of the operations within an OCG. So, OCG is essentially a directed acyclic graph where the nodes are operations and edges are data dependencies, right, dependencies between operations. So, which is dependency on data. So, we label nodes of G in topological order and assign a C step to each level. So, let us see one such type of resource and constraint scheduling, and it is called, very simple, it is the ASAP schedule. So, how does it work? It is generated from the DAG by a breadth first search from data sources to sinks. So, you start with the highest nodes that have no parents in the DAG, and then you assign time steps in increasing order as you proceed downwards. The simple rule here is that a successor node can execute only after its parent has completed execution. Let us see. So, for understanding this and the other examples in the scheduling in scheduling what we will study, we will take this basic block. So, this basic block is essentially for a design of a differential equation. So, here you have these operations x1 equals to x plus dx, u1 equals to u minus 3x u dx minus 3y dx, y1 equals to y plus u into dx, and c equals to x1 less than a. So, these are the the statements within the basic block. Now, for that we will first obtain the data flow graph. So, if you obtain the data flow graph, let us see what is this node performing. This node is performing 3 into x here. This node 2 is performing u into dx. Node 3 here, the third, node 3 is performing this whole thing, 3 into x into u into dx. On the other hand, the node 6 is performing 3 into y, node 7 is performing 3 into y into dx, and then here node 4 is performing u minus this whole. Likewise, you see that this graph here correctly represents all the operations with including the correct dependencies in the basic block that we have here. So, therefore, for the basic block on the left, this one, the graph on the right is the data flow graph representing this basic block. From the basic block, as we said, we obtain the operation constraints graph. So, we remove all the input variables, or we remove all the variables and only show the dependencies between the operations. So, this one is the data flow graph and this one is the corresponding operation constraints graph. Okay. Using this, we generate the ASAP schedule. How? We said, how does the ASAP schedule work? We go from the highest nodes downwards with the simple rule that we try to schedule as quickly as follows, as quickly as possible, as early as possible, with the constraint that a successor node cannot be executed unless their parents have been executed. So, for example, here one, because this one is a dummy node, this is not an actual node, 1, 2, 6, 8, 10 all can be executed in the same time steps, because they have no parents, or means same as saying that their parents, they have no more dependencies. So, they are all ready to execute, and because you have unlimited resources, this is resource constraint scheduling, you can schedule all of them in time step 1. Now, in time step 2, 3 can be scheduled, because in time step 1, assuming that all these operations are take one time step, we are using the simple assumption that these are all one time step or one cycle operations. So, assuming that all these operations are one cycle operations, 3, 7, 9, 11 all of them can be done in time step 2. However, node 4 cannot be executed in time step 1 or time step 2, because node 4 cannot be executed unless time step 3, sorry, unless node 3 completes operation. Okay. So, node 4 can be performed in time step 3, and finally, node 5 can be performed in time step 4. So, this is the earliest possible, or the ASAP schedule, right, and we get the ASAP schedule here, the same ASAP schedule that we explained in the last slide. The ALAP is an opposite to the ASAP schedule. It is very similar to the ASAP schedule, but we start from the exit node or the sink node and go from the bottom, we go upwards, from the bottom upwards. Now, ALAP solves the latency constraint problem. So, if we are given that this is the deadline before which all operations should be completed, we assume that the last operation will always be completed in the last time step that is available. So, for example, if we assume that the here we said that in the ASAP schedule all operations must be completed within time step 4, right. If we assume that we want to generate an ALAP schedule with a time constraint of 4 units of time, the same as produced by the ASAP schedule, then we can have an ALAP schedule like this. Why? Because at time step 4 we can perform operations 5, 9 and 11, because we start from the bottom and go upwards. We say that which are the nodes which do not have any dependent operations, or all the dependent operations have already been scheduled at later time steps. So, 5, 9 and 11 are 3 such operations in our operation constraints graph which do not have any further dependent nodes. So, all these nodes are performed in the last time step that is available, which is the 4th time step. Then, however, 4, 7, 8, 10 all these nodes cannot be executed in the last time step. Why? Because on all these operations there are dependent operations on 4 and 5 depends on 4 and 7, 9 depends on 8 and 11 depends on 10. However, because 5, 9 and 11 have been scheduled in time step 4, we are free to schedule 4, 7, 8, 10 in time step 3. Then time step 2 we schedule 3 and 6, and in time step 1 finally we schedule 1 and 2. Okay. So, this is the ALAP schedule with the time constraint being 4 with, however, here also as in the ASAP schedule we assume that we have unlimited resources. Because we assumed we have unlimited resources, we could without considering how many resources we have been able to schedule 3 operations in the last time step, 4 operations in the second last time steps, likewise, right. So, here also similar to the ASAP schedule, we are not considering any bound on available resources. With this understanding, we will understand mobility. Now, these it may look that the scheduling strategies that we have looked till now, these are sort of not practical. When do we have a situation when there are no constraints on available resources? However, the understanding of these schedules are important, because these properties of the times, the ASAP and the ALAP times that can be associated to each operation in the ASAP and ALAP schedules will be used later for the other algorithms, which are slightly more complicated ones. One important parameter for each operation that we can obtain from the ASAP and ALAP schedules is called mobility. Now, the mobility is defined as the difference in time between the ALAP and ASAP schedules. So, the ALAP schedule, let us say, says that, for example, we will take an example in the next okay, let me tell you that, let us say that the ALAP time says that the 7th node can start execution or can be executed fully, because it takes only one time step at time step 7. So, sorry, at time step 3, the 7th node at time step 3, this is the ALAP time. So, the ALAP time of node 7 equals to 3. What is its ASAP time? If you go back, its ASAP time is 2. So, the ASAP time is 2. So, ASAP of node 7 equals to 2. So, the ALAP minus ASAP is 3 minus 2, which is equal to 1. So, mobility of node 7 can be 1, can be said to be 1. So, mobility of node 7 is 1. Similarly, for others we can obtain. So, mobility gives an idea of the slack on start time that we can possibly have given on in any case. Here it is unconstrained resources. It is also called, mobility is also called the degree of freedom. That means, the number of cycles by which an operation can be moved upwards and downwards. This is the maximum by maximum this many time steps I can move the operation lower or upwards or lower in the schedule. Okay. If we have this a time constraint of 4, we said that this must be performed in the 4th time step, this should be performed in the third time step in the ASAP schedule, this will be performed in the 2nd time step in the ASAP schedule, and this one is performed in the 1st time step in the ASAP schedule. In this, so what do we have? We have said that if we have this schedule, in this, if we have a constraint of 4 time units, then V1, V2, V3, V4, V5 all have mobility 0, they cannot be moved. Means it says that you must schedule operation 1, this node 1 at time step 1. If you do not schedule operation 1 in time step 1, you will miss your time bound or deadline of 4 units. Similarly, the same will happen if you do not schedule operation 2 in time step 1. The same will happen if you do not schedule operation 3 in time step 2 and exactly at time step 2, nowhere else. Same for 4 and same for 5. So, all of them have a mobility of 0. For 6, however, the situation is not that. You can schedule 6 either at time step 1 or at time step 2. If you for example decide to execute node 6 in time step 2, you have the liberty of scheduling node 7 in time step 3. However, still means not however, still ensuring that you will not have to suffer a deadline miss. So, you similarly 6 and 7 both have a mobility of 1. Operations with mobility 2, 8 can be scheduled in time step 1 or time step 2 or time step 3. If you decide to schedule node 8 at time step 3, you must schedule node 9 in time step 4. However, if you decide to schedule node 8 at time step 2, then you can schedule node 9 either in time step 3 or time step 4. So both 8 and 9 have maximum mobility or degree of freedom of 3. Similarly, for node 10 and node 11, they have mobility or degrees of freedom of 3. With this, we will now look at the second, time unconstrained scheduling. We have seen resource unconstrained scheduling, now we will look at time unconstrained scheduling. So, what do we want to do? We want to schedule operations within a basic block such that all operations can be performed in correct sequence using minimal hardware resources in unlimited time. So, if you have unlimited time, you can possibly use a single hardware resource if that is available, and if you have a hardware resource that performs all operations and perform all of them, because you have unlimited time, you can choose to perform only one operation at one time step. However, the operation that you choose to perform at a given time step must satisfy precedence. So, therefore, you need a serialized topological sort of the elements in the DAG. As we said, we showed one. Similarly, for this case here, this could be a sorted sequence 1, then 2, then let us say 6, then let us say 3, then let us say 7, 8, 10, 9, 11, say then 4 and 5. So, this is a sorted sequence from up to down, right. So, if you perform, let us say choose to perform, because you have unlimited time, one operation in each time step, then if you perform in this order, that means in time step 1 you perform 1, in time step 2 you perform 2, then in time step 3 you perform 6, then in time step 4 you perform 3. If you perform the operations in this order, you will have a correct schedule which satisfies it means it will produce a correct result. However, it will take a lot of time, because you however, in this case you have unconstrained time. So, this is not an issue. Okay. After this, we look at a more practical scheduling strategy, the resource constraint scheduling. In resource constraint scheduling, we schedule operations within the basic block such that all operations can be performed in correct sequence in minimal time using the available number of hardware resources. So, now resource is constrained, and resource is constrained, that means it is not minimum resources, you have constraint, you will say you have 4 resources of this type, 5 resources of another type, but you cannot use more than 4 resources of type 1, you cannot use more than 5 resources of type 2. Such constraints are given to us, and satisfying these constraints we need to schedule all operations within the operation constraints graph in minimum time. This is the resource constraint scheduling problem. This problem in most practical scenarios is NP hard, and we will look at a fast heuristic solution strategy called list scheduling. Let us now look at the list scheduling strategy for resource constraint hardware scheduling within a basic block. List based scheduling, it is one of the most popular scheduling methods, and it is often said to be a generalization of the ASAP schedule, because if you do not have resource constraints, it produces the same results as the ASAP schedule. How does it work? It first generates a priority list of ready nodes. So, at any point in time, it generates a priority list of ready nodes. So, which nodes are said to be ready? Those nodes which either do not have any parents or their parents have already been scheduled. So, these are ready nodes at any given time during partial schedule generation. At each iteration of the algorithm, we try to use up all resources, because we have a certain number of resources that is given to us. We use up all resources by scheduling operations at the head of the list. Why head of the list? Because it is a priority list. That means, we have sorted the list in some order, we have a priority order in the list. So, in the head of the list we have the highest priority nodes. Now, if you have conflicts, the operation with the highest priority is scheduled first. Let us look at more deeply in the exact pseudocode of the algorithm. So, we start with time step 1, L equals to 1, time step 1. So, this is time steps. Then we repeat for each type, for each resource type k equals to 1 dot dot up to. So, let us say k equals to 1 represents multiplication, k equals to 2 represents addition, etcetera, or if multiplication is done by a multiplier. So, it is a multiplication operation. So, multiplication and this one is addition, right. Now, you determine candidate operations. So, this one represents a multiplier, this one is an adder, let us say. Similarly, for other types of resources you have up to nr types of resources, you have nr is the types of resources. For a given type, for the kth type, you find out candidate operations which are ready, but still not scheduled. So, let ulk denote the candidate ready operations of type k at time step L. So, ulk ready operations, ready to be scheduled operations, ready to be scheduled operations of type k, resource type k at time step or C step, time step, also called C step L. So, you determine candidate operations and then you determined unfinished operations. So, here you are assuming that not all operations can be completed within a single clock cycle. So, you can come to a clock cycle and say that you have a certain set of operations which have been still running, have started in an earlier time step, but are still running. So, some of the resources of type k will be used up by unfinished operations. So, all these operations which are unfinished. So, you have TLK operations of type k which are unfinished, which are currently running and hence occupying the resources of type k, and you only have a certain number AK of resources. So, AK, what does it say? AK, number of resources of type k, number of resources of type k. Similarly, for all types you will have so A1, A2 dot dot up to ANR. So, where AK represents the number of resources of type k. Now, select a subset SK of from UK. So, UK gives me what? The set of ready to be scheduled, the entire set of ready to be scheduled operations of type k at time step L. Now, SK, we choose a subset SK. Obviously, this SK we have still not talked about priority, but let us say this SK will be the those subset of operations from ULK which are of the highest priority in ULK. So, you can have multiple operations that are ready to be scheduled in ULK. Among them we choose a subset SK of the highest priority operations such that SK plus TLK is less than equal to AK, and essentially if we use up all resources, and if use up all resources, and if Sk plus TLk is greater than Ak, you can have this less than equal to be equal to. On the other hand, it could be that you exhaustively means Sk is equal to mod of ULk, that means all operations, mod of Sk is mod of ULk, that means all operations in ULk has been in Sk plus TLk are the unfinished operations, but you still have some resources available, then this less than equal to. So, in the general case it will be Sk plus TLk less than equals to Ak, this condition has to be satisfied. However, you will try to use up all resources if you have ready to be scheduled operations. So, if it so happens that you have sufficient number of elements in Sk such that sufficient number of elements in ULk such that ULk plus TLk becomes greater than Ak, then you will choose such a subset Sk that such that Sk plus TLk equal to Ak, right. So, you use up all resources if you have sufficient number of ready to be scheduled operations. Schedule Sk operations at time step L and you assign the time step, that means the start time of these operations are become L. So, Ti is the start time of operation Vi belongs to Sk. So, for all operations Vi belonging to Sk, you assign you schedule them, you assign a time step to it, and that is what is scheduling essentially means. You assign a time step to each operation, and that is Ti equals to L. After you have done this for time step L, you increase time. So, you do this for all types of operations that are available, operators that are available, then you increase time and go on to the same thing, doing the same thing. We take an example and understand this. Again, we had this data flow graph, the operations constraint graph, only this the dummy node has not been shown here. So, this is the dummy node, and this is the essentially the operational constraints graph, and you have this schedule that we have generated. So, how do we get this? So, let us assume that you have two multipliers and you have two ALUs which perform addition and comparison, let us say. Then you give priority labels below each node. So, we said that the first step is to generate a priority list, and what is this priority list? For example, let us say this priority list tells me what is the below each node. So, we have this priority list below each node, right. So, what is this priority list? You can say that it is defined by the amount of workload, that the amount of workload below this node in the path. So, this one has been given a priority value of 4. Why? Because 4 operations must be completed in order to complete this path. For this operation has been given a priority of 3, because 3 operations must be completed in this path. Here this operation also has been given a priority, this node 6 has been given a priority of 3. Why? Because 3 operations must be completed to go to the exit node. Here the node 8 has been given a priority of 2, because 2 operations must be performed to go to the exit node. So, amount of workload below a given node, including itself, that determines the priority. We have determined priority in this way. Why? Because our objective is to complete early, and the priority essentially says that these operations are more urgent to be scheduled earlier. Because their priority is higher, we want to schedule them early, because if you delay the scheduling of these operations, subsequent dependent operations will be delayed further. So, this gives us our priority. So, we have given priority in this order, and then after we have determined priority, we go over the time steps. So, see step 1 or L equals to 1, here L equals to 1. The first type of resource, let us say multiplication resource, k equals to 1 represents multiplication, let us say multiplier, So, our at the first time step our candidate operations are V1, V2, V6 and V8, all these are of type multiplication, right. Then among them which are the highest priority, we cannot schedule all of them in the first time step. Why? Because we only have 2 multipliers, although we have 4 ready to be scheduled operations. So, what will we do? We will take the highest priority operations among them. So, who are the highest priority? V1 and V2 are of the highest priority, they have priority value 4, urgency value 4. In comparison, V3 and V8 have urgency values 3 and 2. So, we choose V1 and V2 because their labels or priorities are maximal, and then we therefore schedule them at time step 1. V1 and V2 are scheduled at time step 1. So, T1 equals to 1 and T2 also is given 1. Now, we come to the next type in the iteration, in the next it means in the iteration. So, for k equals to 1 we have done, now we do for k equals to 2, we have 2 types of resources, multipliers and adders. So, how many resources means how many available candidate operations do we have for the addition operation? We only have one, which is 10, this is ready to be scheduled, that is. So, U12 is 2 and therefore, S2 is also 2. We have 2 operations, we have one operation which is ready and we have 2 resources. So, hence we can easily schedule without computing anything else this V10 in an adder resource. So, at time step now from time step 1 we come to time step 2. So, we have seen now time step 1 for k equals to 1 and k equals to 2 for time step 1. So, this we have seen. Now, we come to time step 2. At time step 2 how many the ready operations now are V3, V6 and V8. Why? V3 has become ready because both V1 and V2 have already been scheduled, V6 and V8 were already ready, but could not be scheduled in the previous time step because we did not have enough resources. Now, what do? We see that among these V3 and V6 have higher labels of 3 or priority 3 compared to V8. So, we schedule V3 and V6. Sorry, this is time step 2. Then at time step 2 for k equals to 2 we see that now operation 11 has become ready because operation 10 has already been scheduled and therefore, we schedule operation 11 at time step 2. Likewise, we proceed. For the time constraint version of the same scheduling problem, we take the same resource constraint means same list scheduling and perform the time constraint version of the scheduling problem. Here we start by assuming that we have one resource of each type A1, A2 dot dot up to ANR. We have NR types of resources. All these are we have only one units of each type of resource, and then we generate an elapsed schedule for the given constraint lambda. If the elapsed time for the start node, so T0L is the elapsed time for the 0th node or the start node. If the elapsed time is less than 0, what does it indicate? It indicates because see for a given resource constraint we are generating the elapsed schedule from the exit node upwards. So, while doing that we have found that the elapsed time, that means the latest start time of the start node has become less than 0. So, that means I must even if I start at time step 1 I will miss a deadline. So, therefore, no schedule exists if T0L is less than 0. Then again we proceed time step wise. We start with time step 1 and then repeat. For each type of resource, very similar to resource constraint scheduling, we determine candidate operations and then we compute slacks of these candidate operations. Now, slacks means how, so if my current time step is L and TIL is my latest time step at which I can possibly schedule this operation for a given operation Vi. I have the elapsed time to be TIL, then TIL minus L, TIL minus L gives me what? Gives me the current slack. I am means I can still possibly schedule the ith operation without violating deadline if I schedule TIL minus L time steps later than the current time step. L is the current time step, TIL is the latest time step by which I must schedule the operation Vi. So, TIL minus L is the current slack value Si. So, for each candidate operation in ULK, I determine the SI values and then I schedule candidate operations with 0 slack and update AK. That means, we are scheduling candidate operations with 0 slack. So, it could be that you have current you have started AK equals to AK with the value of 1 and now you find at a given time step that you have 3 operations in ULK having SI equals to 0. So, you must schedule all these 3 operations in the current time step, otherwise you will definitely miss a deadline. So, how can you do that? The only possible way you can do that is by increasing the number of resources that you must incorporate within the design. So, you increase update AK and say that because you have 3 operations which have slack 0, AK must be equal to 3 now. So, you update AK. Then you schedule candidate operations requiring no additional resources. After you have scheduled 0 slack operation, now let us say at time step L you have made AK equals to 3. Okay. Then let us say at the current time step, in the time step L plus 1, AK equals to 3. So, you have 3 resources. Now, you have only one operation having slack 0. If you have one operation on slack 0, you still have 2 remaining residual resources. So, you have 2 remaining residual resources. What do? You take these 2 remaining residual resources and then you do not have currently you do not have any operations having slack 0, but then you can schedule the least operations having the least slack higher than 0, albeit you can schedule operations with the least slack, but not taking more than the available resources. For example, currently at L plus 1, if you have AK equals to 3 resources and you have SI equals to 0, only one operation having SI equals to 0, but then sorting it from lowest to highest, you have another operation having SI equals to 1 and another operation having SI equals to 2, and let us say 3 more operations having SI equals to 3 or higher, right, I1, I2, I3 higher. So, these 2 resources, although do not have slack 0, can be scheduled at the current time step because it will not require any additional resources. So, after you have scheduled all the operations having 0 slack, you schedule candidate operations requiring no additional resources. Then very similar to resource constraint scheduling, you update or increment time and proceed until all operations in the in the basic block or in the operation constraints graph has been scheduled, and then you return the schedule. With this understanding of the different scheduling strategies, we have studied the time unconstrained, resource unconstrained, resource constraint, and then finally time constraint scheduling. After having a look at all these 4 strategies, we come to the end of this lecture.